Hello dear students. So today we are going to start with the next topic, the inner transition elements or F-block elements. Now what are F-block elements? F-block elements are those which involves the gradual filling of F subshell. F subshell get gradually filled in these elements. So F-block elements, they consist of two series. First one is called as lanthanoids, as you can see, lanthanoids. There are 14 elements following lanthanum. Now this is very important, following lanthanum. Although the electron enters or filling of F subshell, it starts with cerium and it ends at lutetium. So there are 14 elements which involves the gradual filling of F subshell. It is followed after lanthanum. Okay, so because lanthanum, this lanthanum is, it closely resembles the lanthanoids, so that's why it is usually included whenever we discuss about lanthanoids. Symbol is Ln. Similarly, actinoids, second series is actinoids. They involve again the gradual filling of 5F subshell, and it starts from atomic number 90, that is thorium, to lawrencium, that is 103. Okay, and again it follows actinium, so they are called as actinoids. Okay, then general electronic configuration of lanthanoids. Our main focus will be first on lanthanoid, so it will involve 4F1 to 14, 5D0 or 1, and 6S2. This is the general electronic configuration for all the lanthanoids. So the filling of 4F, it takes place in anti-penultimate shell, right? The outermost shell is 6S and the electron enters in 4F, which is anti-penultimate. Okay, so first of all, lanthanoids, a table is given in which atomic number, name, symbol, electronic configuration in ground state, then 2 positive oxidation state and 3 positive oxidation state, as well as 4 positive oxidation state is given, along with atomic and ionic radii. So the 15 elements are given now, because lanthanum is also involved in properties, so we will discuss lanthanum also. So there are 15 elements now if we include lanthanum, but the gradual filling that starts with cerium. So lanthanum with atomic number 57, 58 is cerium, then praseodymium, then neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. These are the elements. Okay, actual number that starts from 58 to 71. So the first element is lanthanum. As you can see, the electronic configuration in ground state, it doesn't contain F subshell. It has electronic configuration. All this follows after xenon. Okay, xenon has atomic number 54, so in square bracket xenon will be there, right? So following xenon, so after that 5D1 and 6S2 will be the electronic configuration, right? Then simultaneously for lanthanum, if the 2 electrons, it's obvious that the electrons will be removed from 6S. So in 2 oxidation state, the electronic configuration will be 5D1. And do remember, we are using these symbols Ln. This Ln symbol is the general symbol for all the lanthanoids. Okay. In the same manner, if +3 oxidation state is there, so then 3 electrons are removed, and hence lanthanum will become stable as it will acquire electronic configuration of xenon. Okay, so +2 oxidation state, +3 oxidation states are given. So the first element is cerium, which involves the filling of F subshell. So the cerium has electronic configuration, its symbol is Ce, atomic number 58, and 4F1, 5D1, 6S2. Then likewise, in case when the two electrons are removed, so the electron shifting takes place from 5d to 4f, so it will have 4f2 electronic configuration, and in +3 oxidation state 4f1, so +4 oxidation. So cerium generally shows +4 oxidation state in addition to +3. They have most common oxidation states of +3. As you can see that in +3 oxidation state, they gradually involves the filling up of 4f. For example, for lanthanum it's 4f0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So gradual filling is there. So most stable oxidation state in lanthanoids is +3. Okay, which oxidation state? +3 oxidation state is the most stable oxidation state. Then in the same manner the gradual filling takes place now in praseodymium. 4f3, 6s2, likewise the electronic configuration is given. So I think there is no particular change. Yes, do remember, for example, in 63 europium atomic number 63, it has 4f7, 6s2 electronic configuration. That is, in +2 oxidation state it becomes half filled. F subshell becomes half filled, so it can also show oxidation state of +2. Then gadolinium has 4f7, 5d1 and 6s2, so it will show +3 oxidation state as the most stable oxidation state, because by acquiring that it will have half filled electronic configuration which is stable. Terbium 4f9 in +2 oxidation state, and then 4f9, 6s2 in ground state, so on. Again, it can show +4 oxidation state. So do remember, in addition to +3, +2 and +4 oxidation states are also stable, but they will be only if the species is acquiring stable electronic configuration. Okay, so on. Then ytterbium and lutetium. Now ytterbium has 4f14 and 6s2. So ytterbium will show +2 oxidation state as most stable oxidation state. Okay. Then lutetium 4f14, 5d1, 6s2. So 4f14, 5d1 in +2, but in +3 oxidation state it will have that stable electronic configuration. So the stable oxidation state will be +3. Okay. Now we will discuss about the most important property of lanthanoids, that is atomic and ionic radii. So as you can see in this table, symbols, elements and atomic radii and ionic radii is given. It was also given in the previous table. Atomic radii along the series, right, from cerium to lutetium, generally it decreases. In general there is decrease. The reason is same, that along the period whenever we move, due to increased nuclear charge, the size goes on decreasing, or radii goes on decreasing. The same trend is followed in ionic as well as in atomic. So cerium has 183 picometer, then it decreases, but if you analyze this decrease, there is very minute change. Okay, so this very small decrease in atomic radii results due to lanthanoid contraction. Okay, there is one exception in case of europium. This is basically due to its structure. The structural arrangement is such that its radii expands. Rest there is gradual decrease, and this decrease is very small, just from 183 picometer to 173 picometer. Almost 14 elements they are involved, right? In the same manner, when we analyze in +3 oxidation state, because we have discussed that +3 oxidation state is the most stable oxidation state, so there is gradual decrease, there is no abnormality. Again, this decrease is very small. Now this decrease is very small? The reason is their electronic configuration. In general, they have electronic configuration 4F 1 to 14, right? 4F 1 to 14, and then 5D 0 or 1, and 6S2. Okay, this was the general electronic configuration for these 6S2. Now for this, actually the valence shell is 6S, and the electrons, they enter in 4F. So let us take an example that if nucleus is there and then there are shells like this. First shell, second shell, third shell, fourth. So this fourth shell will have 4F subshell here, and then fifth, and then sixth. So 6S will be here somewhere here, right? As you know that among subshells, S subshell, P, D, and F. What about their shielding effect? So S has maximum shielding effect, P lesser, D lesser, and F has poorest shielding effect. So as a result of poor shielding effect of F subshell, the 6S electrons, they are strongly attracted by the nucleus. Okay, what happens? Due to poor shielding effect of F subshell, the outer electrons, they will be attracted strongly, and as a result, nuclear charge experienced by 6S electrons will be more. And as the electron goes on increasing, that is, from one electron is added, there is gradual increase or steady increase in the nuclear charge, which results in decreased atomic radii, and this steady decrease results in lanthanoid contraction. This is very important, lanthanoid contraction. Okay, this ionic radii, in the same manner, it is given in +3 oxidation state. The overall decrease in atomic and ionic radii from lanthanum to lutetium, that is lanthanoid contraction, is a unique feature in the chemistry of lanthanoids. Now we will discuss about the after effects or consequences of lanthanoid contraction, how it has changed the chemistry of elements. So basically, it has far-reaching consequences in the chemistry of third transition series of the elements. How there is a resemblance in the third transition series to that of second transition series. The decrease in atomic radii is quite regular, as it is more regular in +M3 positive ions. As you can see in the figure that there is regular decrease in ionic radii or atomic radii. Okay. This contraction is of course similar to that observed in an ordinary transition series. We have also discussed the same in transition series where d orbitals are filled gradually, and they also show poor shielding effect, but the change is not that much as it is in case of lanthanoids. The reason was same, that is the imperfect shielding of one electron by another in the same subshell. However, the shielding of one 4F electron by another is less and then one D electrons by another. As a result, there is total decrease or fairly regular decrease in the size with increasing atomic number. Okay. Now we will move towards the consequences of lanthanoid contraction. So this cumulative effect of the contraction of lanthanoid series, which is known as lanthanoid contraction, causes the radii of the members of third transition series to be very similar to those of members of second transition series. As you can see in the figure, this hafnium and zirconium. So zirconium belongs from second transition series, whereas hafnium belongs from third transition series. But can you see the difference that from yttrium to zirconium there is addition of 1 electron and size decreases. It has almost 160 picometers, whereas from lanthanum to hafnium there are 14 F block elements also. So there is a steady decrease, and it is just similar that there is only entry of 1 electron in second transition series, as much atomic size is there, and whereas there are 14 elements which are added, and again the size decrease is almost same. So this has played a vital role in the chemistry of second and third transition series. That is, they have almost similarity in their properties. In the same manner, tantalum and niobium, and these two also have almost same atomic radii, and the atomic radii of second and transition series are almost similar in this case. Okay, then another thing, as a result of lanthanoid contraction, because the variation in size is very small, so they occur together. Their occurrence in nature is together. They cannot be easily separated, so there is difficulty in their separation. So these are the consequences of lanthanoid contraction.